This is my PhD work where we have optimized the operating parameters of a biogas fueled engine. Now I'm just there is a little bit of background here where we have started, why we have started, and what motivated us. So as you know, most of the energy we are using is derived from the fossil fuel, and petroleum based fossil fuels are used mainly for transportation, power generation, and agricultural activities here around the world. And if you look at that BP Statistical Review World Energy 2019, we can identify that transportation sector is the major consumer for the petroleum based fossil fuels. And petroleum fuels, there are some issues with petroleum fuels like depleting reserves of the fossil fuel, intensified energy demand which rises day by day, and rise in the price of petroleum fuel, and of course the pollution part also plays a major role. But then what are the solutions we have, like alternative fuels, renewable fuels from non-fossil carbon resources, exploration of performance improvement methods in those energy conservation and transformation devices, exploration of emission reduction techniques. So these are some of the solutions through which we can address these issues that we have currently. Among the renewable fuels, we have mostly two categories: liquid and gaseous fuel. And mostly gaseous fuels are being considered advantageous over the liquid fuels because of few of the reasons attached to combustion. They had a wide range of flammability limit, and they can form homogeneous mixture. And even we can burn very lean mixture, and the hydrogen to carbon ratio is very high in those gaseous fuels. But we know the issues associated with hydrogen storage and transportation are the major issues. So biogas can, for at this instant, it can be, for this era, we can say that biogas can be considered as a attractive renewable source of energy for mostly developing countries, which consist mostly of CH4 and CO2. We have almost 60% of CH4 and 40% of CO2, along with some other impurities like hydrogen sulfide and nitrogen also. And what are the advantages here with biogas? The advantages, if you look at its physiochemical properties, the advantage is with its auto-ignition temperature and research octane number, which is around 110 and 650. RON is around 110 and auto-ignition temperature is around 650. So these are two major advantages that is qualifying biogas as a fuel, suitable fuel for SI engine. And most effectively, the combustion of such fuel do not affect the net CO2 in the environment, because it already contains CO2. Once we are going to complete the combustion process, the net CO2 emission is comparatively less than other fuels. So for this kind of fuels, we need an energy conversion device. So what I need, like identification of a suitable energy conversion device for biogas to power generation. Mostly we are talking about an IC engine which can efficiently convert the available energy of biogas into work. And currently the available technologies are limited to limited and suitable for LPG and natural gases, and they are limited to high power multi-cylinder engines. And mostly those dual fuel engines are using the engines which are using biogas. They are mostly dual fuel engines that are using in pilot fuel up to 30 to 40%, and yield in high price of biogas fuel engines. Those are manufactured by Cummins, Prakash gas generators. So these are two companies which are manufacturing this kind of engines. Now significant use of there are significant use of low and medium low power single cylinder engines, medium to low power single cylinder engines in the rural and remote areas of developing countries in the field of agricultural and decentralized power production. So if you are going to devise something which will support this part, and the cost will be reasonable. So in that case, we can consider that it is a good innovation. Now, there are some issues with biogas, issues like it cannot be used alone in CI engine, because we have seen the auto ignition temperature is 650 degrees centigrade. So that cannot be, the combustion cannot be initiated when we are using in CI engine directly as a standalone fuel. But it can be used along with the pilot fuels, either it may be liquid or gaseous pilot fuel. It can be used in both CI and SI engine. For gaseous fuel, it is essential to use SI mode because it's an octane fuel, so it should be used in SI engine rather using in CI engine. It can be used in CI modified SI engine, so we can also modify a CI engine and convert it into SI engine, and we can also use biogas with that engine, which can operate at higher completion ratio. But we need some major modifications when we are using when you are converting a CI engine for biogas application, like we need to detach the fuel injection system, incorporate suitable spark ignition system, modification of the engine intake system for air fuel mixing, reduction of CR to an optimum level, developing and governing system to support correct air fuel ratio. So these are the major modifications that has to be done when you are converting an existing CI engine for biogas application. First, as a standalone biogas, when we are considering biogas as a standalone fuel. But rather, when you are going to use an SI engine, we do not have to take much, we do not have to handle much issues, because what we need to do only here, we need to change the engine, the fuel intake system only. We need to have some modification in the engine intake system. That means the carburetor, conventional carburetor, has to be replaced by a gas mixer, and that gas mixer need to be designed properly. Again, with as in the beginning I told you, there are some performance improvement methods which can also positively influence the devising of this kind of engines, like the techniques like variable compression ratio, fuel enrichment method, optimum ignition timing or spark timing, and pollution control methods like excess air supply, exhaust gas recirculation, and catalytic converters. So with this kind of, with the involvement of this kind of technology which is being listed out here, we can also improve the performance of this kind of engines. Now the objective here, where I had done my PhD work, the objective was to devise a low cost 100% biogas fueled SI engine. So since it is not like biogas engines are existing, as I told you, but the price is too high and the power output, it's not applicable to medium and low power single cylinder engines. So the objective here is to devise a low power, medium to low power output range single cylinder engine which can applicable to decentralized power production or in agricultural applications. Now what we have done, we have started analyzing an engine, commercial available engine in the beginning. So a commercial, we have purchased a commercial available engine which is a constant speed CI engine which is converted into SI mode. So firstly, we have done an experimental investigation of a biogas fueled customized commercial SI engine which is commercially available. We have customized this to vary its compression ratio. Then what you have done, we have played with its operating characteristics like compression ratio, brake load, and then we have identified the parameters and we have studied the issues. What are the issues with those kind of engine? And then we have identified issues like derating of engine power, inefficient governing system, and then based on that we went further and we work on a second engine which is a research engine setup where we can use different kind of fuels. It can become that is what is called a variable compression ratio research engine setup. So in that engine we can play with the compression ratio, we can play with the ignition timing, we can use fuels like diesel, we can use fuels like petrol, hydrogen, methane, everything we can use it there. But some modifications we have to do in order to accommodate those fuels. So what we have done, we have used this engine, the the second engine, which is a VCR-SI engine, and then we have done some baseline study with gasoline, because this engine is mostly designed, and the uh, characteristics of those engines are mostly designed for gasoline only, but we can use different fuels in this engine. And to record to have a reference line, we have first operated this engine with gasoline, then we have done a baseline study with methane, then we also done with a baseline study with biogas. At a fixed comparison ratio, we have used 3 different fuel and we have compared it. Then what we have done, after the comparison, we found out that what is the issue with this engine when you are operating with biogas. So like we know that methane, when you are talking about methane, it's pure methane, 100% methane, but biogas contains 60% of methane, so there will be obviously derating of engine power. Gasoline also, it is the power output of those engine when you are using gasoline is obviously high. But in order to accommodate these losses, can you do something? Can we do something? So for that we have identified the issues, identified the issues associated with the VCR engine when you are operating with biogas. And at the third stage, we have purchased a normal SI engine, like Honda GX200 engine, which are mostly used for land movers. And then we have in this engine, the issues what we have identified in the second engine, which is a VCR-SI research engine setup. We have done some kind of analysis here. We have played with the operating parameters. We have identified the optimum operating parameter in the VCR-SI engine, and we have implemented those parameters in the third engine, which is a pure SI engine. It is pure commercial SI engine, which is applicable for land movers or some other kind of application. It's a Honda made engine, and so the operating parameters what we have optimized in this engine we have implemented here. Like we have found out an optimum operating compression ratio for the biogas when it is operating in CR, when it is operating with the VCR engine. We have identified the ignition timing, we have identified the optimum air fuel ratio, we have identified the throttle position, and then we have fixed all those parameters in this engine, and then we have studied the third engine again. So 3 different engines are there, but what is the common between these 3 engines? The rated power output of all these 3 engines are constant. So the first engine is designed to produce and brake power of 4.4 kilowatt. The second engine is designed to produce and brake power of 4.4 kilowatt, but the third engine is somehow designed to produce an operating the power output of around 4.3 kilowatt. Okay. So then once we have implemented all those optimum parameters in the third engine, we have compared all these 3 engines with the maximum output condition. So that is what is the summary of my PhD work here. So I will take you step by step to each and everything. So this is what an commercial biogas engine, which is a normal, very normal engine, which is installed near a biogas plant. We have here in outside our IIT campus. We have designed a setup like I'll also go further and show you what are the modifications we have done in this engine to for capturing all the parameters. And this is the VCR-SI engine we have in our transit complex. This is the second engine and this is the third engine. This is both of these setups, engine 2 and engine 3 engine setups are in transit complex. Next is about the fuel properties, because we are dealing with 3 different kind of fuel. We are going to compare all these fuels, gasoline, methane and biogas here in this engine. Because it's a VCR research engine setup, we are going to compare all the fuel here in order to get a baseline so that we can compare when we are designing it. Okay. So these are the properties of gasoline and methane biogas. If you look at some of these things like stoichiometric air fuel ratio, you can see it's 14.7, here it's 17.23, here it is 5.51. All these are calculated values. And if you see the research octane number of methane is higher than that of biogas, and it's higher than that of gasoline also. Flame sheet, if you see the auto ignition temperature, Auto ignition temperature is around 650 degrees centigrade. Here it is 540 to 600. Here it is 257, and flame speed is in biogas is very low, which is a very negative point about biogas. Some of these values we have calculated, some of have taken from the reference. Now the biogas what I am going to use, we have analyzed its composition throughout 2-3 years. We have taken the average of that, because the digester what we are using, the biogas produced from that digester changes with the ambient temperature, composition and other values. We had N2 and H2S. We cannot do anything with N2, but we can scrub out H2S moisture from this biogas when we are using it, because if you are not going to scrub H2S and moisture, it is going to damage your engine component. So we have also designed a few devices to clean H2S and moisture by taking only this indigenous materials, like for scrubbing H2S, we have used annealed steel chips. We have packed in a column, pass the gas, pressurized gas in that column, and at the end we have compared the composition of the gas which is passing through that annealed chips column, steel chips that we are getting from turning and milling. So those steel chips are being used there to filter out H2S. Similarly, we have used blue silica gels to capture the moistures. So after refining it, so let's say this is the biogas digester, which is the site. It's a digester which is buried under the ground, and the cubic capacity of this digester sorry, each digester is of 3 meter cube. So we had series of digesters, like 4 digesters we had, around 12 meter cube. So it is producing 12 meter cube of gas per day. So we have used it, and this is that engine setup. The picture is not clear, but we'll see the line diagram later on. We have attached an crank angle encoder here. This is exactly a biogas generator which is manufactured by Prakash. We have done some modification in the compression ratio. The rated compression ratio of this engine, when as defined by the manufacturer, is 13.94, but in order to see what is the effect of the compression ratio on all other parameters, we have done little modification at our end. And then this generator has to trap the in-cylinder pressure and temperature and the crank angle. We have attached a crank angle encoder here, and then a pressure sensor here in the engine cylinder, inside the engine cylinder. And then for measuring the gas flow, we have a biogas flow meter. Airflow, we have a U2 manometer, and then we have a manual load bank, which is consisting of an watt meter, load panel, and voltmeter and ammeter. From there we have calculated what is the electrical load, and then we have back calculated the engine torque and efficiency. So it's again a water cooled engine. Now we see this is the block diagram, where now the most important thing is here that it's a constant speed engine. It's not a variable speed engine. So we had a governor here, and this governor is controlling the throttle valve basis on the load on the engine. What much the amount of, if you are going to increase the load on the engine, it's simultaneously what is happening, the governor which is attached to this flywheel is going to control this throttle valve so that more amount of fuel can be entered to the engine. This is that biogas digester, 4 biogas digester, which is connected to a integrated biogas storage unit. And then it is attached to the moisture filter, and then H2S scrubber, and then it passes through the biogas flow meter to the engine. This is the air drum, and then it is connected here. Now what we have done, we have changed the compression ratio of the engine. As I have told you that the rated compression ratio of this engine was here 13.94, with some attachment of spacer plates and gaskets. We have continuously replaced it and done this kind of experiments there, where you have changed the compression ratio from 10.52 to 15.92, and this is the rated compression ratio of the engine. We cannot alter the ignition timing in that engine, because it's a mechanical ignition, mechanical attachment, where we cannot adjust it accurately. So we left it, we do not disturb it, we kept it constant. With this constant ignition advance, by varying the compression ratio and by varying the electrical load, we have measured the brake power, VSFC, brake thermal efficiency, airflow ratio, volumetric efficiency. We have captured the P theta, and then from there we have calculated the mean gas temperature, net heat release rate, mass fraction burnt, and the emission components, CO2, SC, NOx, and CO. So these are some of the graphs which is here to find out what is the issue with this engine. Now if you see, when you are operating this engine with all this compression ratio, the maximum brake power what you are getting is around 2.9 at CR 15.29, and the maximum brake load what it can take is up to 75%. We cannot go beyond that, 76% around. And at the rated CR, the blue line here, rated CR, again we cannot go beyond 70, up to, we cannot go up even up to 75%, and the rated brake power is within 2.7 kilowatt. However, the rated brake power of the engine is around 4.4 kilowatt, but at the end what we are getting is different here. Now if you see the engine speed, since it's a constant speed engine which is meant to provide which is designed to produce electricity, and that generator has to be rotate at a constant RPM, because if the RPM is going to fluctuate, the V and I coming out of that generator is going to fluctuate. So in that case it should remain constant, but it is not remaining constant here. If you can see, when you are going to increase the brake load up after 50% brake loading, there is a deviation of engine speed around 10%. So this is what is one more observation we have seen there. Now rest are thing fine, but if you see the maximum brake thermal efficiency, it's around only 18% when you are operating it at CR15. Volumetric efficiency is very low, it's around 28% only. Now these are some of the pressure data, in cylinder pressure data, where this is what is also supporting our what we have obtained in our performance analysis part. Now if you see here, the data are a bit non-continuous here, because here only we can able to capture 10 cyclic data. In each cycle we are able to get 720 data point, and again 720 into 10, that is 720 data points only in between 0 to 720 degrees. So it's not much accurate in this case, but we do not have any kind of support in that time. So that's why we have got this data here. And if you see what is happening at this point, the peak cylinder pressure at 50% loading condition, the peak cylinder pressure is only about 14 bar here at around 50% brake load condition at CR10, sorry, this is CR10, and if it is CR15, the peak cylinder pressure goes up to 24 bar, and the peak cylinder pressure keeps on shifting towards the expansion stroke when you increase the brake load. Now if you see the brake load here 76%, now when you are going to increase the brake load, the peak cylinder pressure is going to shift towards the expansion stroke. And of course when I have only taken 50% brake load condition, because we have seen that up to 50% load only it is working fine. After that there is a deviation in the engine speed, that's why I have only placed this one. Now if you see the mass burn fraction here, this is the time, like rapid burn angle. Rapid burn angle is the duration of duration in which the fuel starts, the combustion initiate, the combustion propagates, and it ends up to 90%. The duration between 10% of mass burn fraction and 90% mass burn fraction is called rapid burn angle. So if we can see here that rapid burn duration is going to reduce when you are increasing the compression ratio. Now if you the CO emission, SC emission and the NOx emission is here, and if you see, like, the CO emission is reducing when you are going to increase the compression ratio. SC emission is also reducing at CR15, and but there is NOx emission at higher compression ratio. Now what is the final judgment in this observation? The engine operating at the rated CR, which is 13.994, and maximum brake load condition 74%, declined the rated speed of the engine by 9% and deteriorated the engine power by 34%. Then this is one of the major observation which need to be take care. Then the next one is the maximum achievable brake power, brake thermal efficiency of the commercial biogas engine that we have taken is only 2.88 kilowatt, and 14.84% is its brake thermal efficiency. If you see the CO, SC and NOx emission, at the rated CR, the CO emission is 0.11%, SC is 116 ppm, and NOx emission is 151 ppm. So these are the issues that we are going to address in our next step by using this variable compression ratio engine. But the issue is what? We do not know at what compression ratio we have to operate. We do not know at what ignition timing we have to operate the biofuel in this engine. We do not know what should be the air fuel ratio that has to be maintained in this engine. So first of all, we need to find out that, and then we can have a range and play with that. So what we have done here, so if you see the engine setup here, it's a 4.5 kilowatt it's a engine single cylinder 4-stroke multiple SI engine, which is able to produce 4.5 kilowatt at 1800 rpm when operated with gasoline only. It's the rated engine capacity at gasoline, with gasoline. And we have the rated CR, it's a VCR engine, so we can vary the compression ratio. But when you are going to vary the compression ratio of this engine, the rated VR of the variable VCR range of this engine is 10 to 18, 10 to 17. But when you are using biogas, we cannot, we have seen literatures, we cannot go beyond 14, 15. So we need some lower range and higher range in between 14. So again, we have attached and we have modified the VCR mechanism there in the engine, and from there we are able to operate the engine in between 8 to 14. Now in this case it's 16 to 10 for this experiment, and the next stage we have varied in between 8 and 14. As the cubic capacity is 661, and we are using, like if you see there, we are using we have transporting biogas to the lab with the help of balloons. We are using a compressor here to compress it around 2 bar, and then we are able to supply here through a diaphragm pump attached to the engine. The diaphragm pump is operated with the help of you see the diaphragm pump. So it's an intake biogas induction mechanism where we have H2S scrubber, moisture trapper, and then a compressor, pressure regulator, fuel meter, and a diaphragm pump. So this diaphragm pump has 2 sections along with a inbuilt heater. There is a driver section and a driven section. Driver section is operated with the pressure drop in the engine intake manifold. When there is pressure drop, it attract or it pull the diaphragm towards the driver section, so that there will be pressure drop in the driven section, and by that what will happen, the biogas will flow from here to biogas mixture. And there is a heater here which is connected with the exhaust from the engine, so the biogas will be again ultimately heated and supplied to this biogas mixture which is connected here. And similarly we have we have some measuring techniques. We have attached some instrumentation here, pressure sensors and crank angle encoders and throttle position sensors with this engine, so that we can record the required data. This is the VCR mechanism what we are talking about. So we have formulated some formula to find out the gap that has to be maintained in between the piston top and the liner top. So this is the gap which is like 1.8. So this is the gap between the piston top and liner top. If the gap is maintained properly, we can able to achieve the compression ratio what is being listed here, and that can be maintained by using this lever which is available here. Similarly, now to operate the same setup with methane, we haven't done anything, just but attach on CS4 cylinder with that, so that it can operate with that. So now, as I told you, that we do not have any clue to operate at what compression ratio and or to operate at what ignition timing. So in the base experiment, what you have done here in this engine, we have found out what should be the compression ratio and what should be the ignition timing, so that this engine can be operated with biogas and methane. And then we have compared the same engine with gasoline, methane and biogas, so that we can find out a list of range of ignition timing we can play with further to optimize the engine for biogas application. So here there are some basic results in that engine. So I'm just going to tell you what we have found out here only. So here what we have found out, we have operated the engine with biogas at a compression ratio 10, and then we observed that at CR10 we are able to find out the optimum ignition timing at 40-degree crank angle before top dead center. So it's because the maximum brake torque what we are observing here at 40-degree BTDC. Similarly, if you are going to vary the speed, also there is no much variations here, like 39, 40 and 41. So 1 degree variation is there within the speed range of the engine. And from there we have understood that if I am going to operate the engine at CR10, the optimum ignition timing should be 40. Similarly, to support this, we have done the combustion analysis, where we can able to find out whether the area under the PV diagram what you have obtained and what you are claiming to be the best, because we are getting maximum brake torque there, here, and maximum brake power also here. So it should also reflected in the combustion chart. So we have calculated the area under the PV curve, and we found out that the area under the PV curve, like IA40, if you see, it is highest 3264.94. The area under this curve is highest. So we can say that this is the ignition timing with which we are getting maximum power. Now, similarly, for the biogas fueled engine, we have also got the optimum ignition timing, where we have seen that ignition time when you are operating at 40-degree crank angle BTDC, you are getting the maximum brake power and brake torque. That is also supported by the combustion analysis, where we are getting maximum brake area under the curve, PV curve, at ignition at IA45. So it is, if I am going to advance the ignition timing 45 degree before TDC, then it is giving me the best result, best brake torque and brake power. I'm not going to the combustion here. Now, this is what is comparison of those three fuels in the same engine at CR10. So if you see here, this is biogas, this is methane, and this is gasoline. Now if I am going to compare, obviously, and as we know that the engine operating with gasoline will have maximum brake power and brake torque, and followed by methane and biogas. The same thing has been observed here. But what is the thing that has to be noted here is the shift of pressure peak. When you are operating the engine with biogas, the pressure peak is shifted by 4-degree crank angle compared to the gasoline. And if you see the area under the curve also, the maximum brake power, maximum area under the curve at when you are operating the engine is with gasoline is highest, and followed by methane and biogas. Now this is where from where we have understood that now the engine, that the VCR research engine, can be operated with biogas, methane and gasoline, and we have some reference data at the base compression ratio. We found out what is the ignition timing with which the engine can now operate. What is the range of ignition timing with which the ignition time the engine can operate. But as I told you that the auto ignition temperature of biogas is very high. It can operate at, the engine can be operated at higher compression ratios. So in order to find out the optimum compression ratio and its corresponding ignition timing and its corresponding equivalence ratio, again we have designed some of the experiments where we have changed the compression ratio, kept the throttle position constant, but if you have seen the previous slides, part throttle position is not going to affect much, so we are operating the engine at wide open throttle condition. Keeping the spark time, we are varying the spark timing from 23 degree to 53 degree. This is the range through which we can upper and lower range we can say. If you are going beyond below 23, the engine is going to there is misfire, and if you are going to above 53, the engine is going to knock. So we are operating in this range, and then we are also varying the engine's fade, and then we are getting the parameters. Now to see here what we have done, we have varied the ignition timing and also varied the compression ratio. If you see one of the compression ratio, let's say this one CR12. Now if I'm going to increase advance the ignition timing, the maximum brake torque is going to increase here. So the maximum brake torque that we found is around 24 Newton meter at 33 degree BTDC at CR12. Similarly, for each and every compression ratio, we have listed out what is the maximum brake torque timing and what is the maximum brake power output that can be produced at a particular compression ratio. So, but it has to be supported. It has to be supported by the combustion and emission analysis. If it is not being supported by combustion emission analysis, it is not going to be worth. So if you see the brake thermal efficiency, as I told you, like this is the list where if I am going to operate the engine at CR8, my MBT timing should be 53. If I am going to operate it at 10, my MBT timing should be 45. If I am going to operate it at 12, corresponding it is 33. And if I am going to operate at 13 and 14, it should be like 29 and 25. But at what it has to be operated, that we have to find out. Now if you see the brake thermal efficiency, the brake thermal efficiency is maximum here at 33 degree BTDC at CR12. So this will give us an idea that even if you are going to increase the compression ratio with an equivalence ratio of, I haven't mentioned here, with an equivalence ratio of 0.79 to 0.8, low equivalence ratio, the engine is not going to produce much power or torque at higher compression ratio. So the limit is CR12 here. Similarly, if you see the BSFC, brake specific fuel consumption, is minimum here at CR12 when you are operating at 33 degree BTDC. Now these are some of the combustion analysis. I am not going to talk about it right now. Now this is what, if you see the same analysis, because we cannot blindly say that at 33 degree BTDC it is producing the maximum brake torque. It has to be supported by some combustion analysis. If you see this mass burn fraction and the PV diagram here. Now the area under the PV diagram we have calculated here at ignition advance of 33 degree crank angle at CR12 when you are operating at an equivalence ratio of 0.79 to 0.8. The area under the curve is maximum here, and it's around 2556, which is maximum among all the ignition area covered by the all ignition advance. Similarly, if I am going to the mass fraction burnt, the at angle 30 at an ignition advance of 33 degree crank angle VTDC, the rapid burn angle, the duration of burning between duration of crank angle in which the mass burn fraction is between 10 to 90% mass burn fraction is being achieved. That is being achieved within like 24 degree crank angle. So within and duration of 24 degree crank angle, the mass fraction burnt, the delta theta v, which is rapid burn angle, is being covered. Maximum amount of fuel is being burnt in that duration. So if you see rest of them, they are more than 24. It's 27, 26, 25, 25, 26, 27, 26. So from here also we can say that this is the point, this is the ignition timing that has to be maintained for this kind of engine. Some tables are there. Now if I am coming to the emission analysis, in that case to optimize the ignition timing. Now if you see at CR12, the black one, CR12, the CO emission, if you see the CO emission here, it's in the middle range, not higher, not lower. But one thing we can observe here, when you are going to increase the compression ratio, at CR12 we are getting maximum CO. The CO emission is maximum here in this case, so it will be reverse when it is CO2 emission. Now if you see the SC emission, the SC emission is minimum when you are operating at CR12, and when you are going to increase the compression ratio, the CO emission is highest at CR8, and it is minimum at CR12, and although like CR14 we are getting more than CR12. NOx emission, if you see, NOx emission is at this 33-degree crank angle VTDC, the NOx emission is higher here, CR12. This is because of the temperature effect, maybe. Now this is where we have seen at what compression ratio, what ignition timing we have to maintain. Similarly, the rest of the experiment are being done to optimize the compression ratio, at what compression ratio it has to be operated. So if you see here, like compression ratio, and this is MBT timing, and these are the speed. But because if you are going to vary the speed, the ignition timing also plays and is going to be changed. The optimum ignition timing will change. Since the range of ignition timing is very low here, like 1400 to 1700, the domain is very narrow here, it's not going to create much effect here. But in reality, if you are going to vary the speed, let's say 1700 to let's say 3000, then there will be a variation. But in this case, there is no variation. The maximum brake torque is again observed here at when you are going to vary the speed. The maximum brake torque is observed at 1400 RPMs, because in that condition the engine load is high, speed is low, engine we are going to apply maximum brake load there in that case. So the brake torque output and brake power output is high in that case, CR12. And brake thermal efficiency is high there. If you see, it's around like 32%, and if you see the brake specific fuel consumption, it is 0.65 kg per kilowatt hour. Now there are supported analysis for combustion, the PV curve, where the indicated power and brake power output is being calculated from the area under the curve. And if you see at CR12, now all this, if you see the ignition timing when you are operating this engine, like when you are operating the engine at CR8, the corresponding MBT has to be set up. So I have written the ignition timing is MBT. For each and every compression ratio, the engine is operated at MBT, but in earlier study we have operated it at different ignition advance. Here it is fixed MBT. So when you are operating the engine at a fixed ignition timing, then we are able to trace the plot, PV plot here. So if you see, the indicated power output here is 3.7 and this is 3.0. The rated output of the engine is 4.4. Earlier we are getting around 2.8. So this is what is the improvement here. That's all. And if you see the emission analysis at CR12, the CO emission will be very high at high speed condition. SC emission is low here in CR12. NOx is obviously high, it will be high, because if you see the EGT, engine exhaust gas, the temperature is around 375, around 375 degree. Now all these are what are the work done in this second engine, what I told you is a VCR research engine. So what we have done only, we have got the third engine where I told you it's a commercial SI engine, which is applicable for, which is mostly used for the lawn mowers. So we have converted that engine to operate with biogas. So as I told you that we need to design a biogas mixture. So what we have done some simulations. We have designed, we have done multiple settings, and there we found out what should be the tube diameter, because this are fixed, because this is connected to the engine inlet. So this end diameter is fixed, this end diameter is fixed. So we have to find out the diameter of this pipe in order to, and we have to look for that what is happening, whether the mixture is homogeneous or not when you are mixing it. This is the pressure profile when we are mixing it. This is the velocity this is the pressure profile, this is the pressure profile where at the thought the pressure is dropping, and the velocity profile if you see. the velocity is maximum there. And if you see the mass burn fraction after at around the exit of this biogas mixture, it's mostly homogeneous, not exactly, but somehow it is homogeneous. With that dimension, we have attached that biogas mixture here in this engine, and then we have tested it. And the optimum compression ratio, as you have seen, we have obtained CR12, but we are not able to implement it here because of limited design specifications. So we have done some kind of adjustment, technical adjustment, where we are able to achieve only CR9. So with CR9, we obtained, we have measured the cylinder, we have measured the volume of the clearance volume, we have measured the clearance volume space, all those things we have measured, but we could not able to attain that compression ratio in this engine because of the manufacturing difficulties. And then there is we have done the performance analysis where we are able to operate the engine in between the speed and a compression ratio of CR 9.53, exactly CR 9.53, and the maximum brake torque output is 12 Newton meter, and the maximum brake power output of this engine is around 4 kilowatt. But the speeds are different here. And then if you see, I have an comparison diagram. As I told you, there will be comparison at the end. So what we have compared, I have taken 3 different engines. The engine 1 was a commercial biogas engine. The engine 2 was a VCR research engine. The engine 3 is that what we have implemented, the optimum parameter where we have implemented it. So in all these 3 cases, when we are operating the engine at biogas, it is producing some maximum power, maximum efficiency, maximum let's say emissions. Okay, so we are comparing that only for this 3 engine by taking this. So this if I am going to compare, this is engine 1, 2 and 3. So if I am going to compare the brake power output, the brake power output of the engine is around like this red one is brake power. So when you are operating with engine 1, the brake power was around 2.8, as I told you. Now when you are operating it with the VCRSI research engine, where we have optimized the parameters, after optimizing, this is the result where we got around 3.6 or 3.8. And now when you have implemented it in engine 3, the brake power is around like similar to the commercial biogas engine, but the compression ratio is low here. When you are operating, if you see, the engine 3 is operating at CR 9.5, MPT is 50 degree crank angle, but if you see this 2, the operating compression ratio is higher than this. Although the operating compression ratio is higher, we are able to match the same brake power with the third engine. The brake thermal efficiency, if you see, compared to the commercial biogas engine, what you have designed, the brake thermal efficiency is around 30%. Here it is around 18%. The maximum brake thermal efficiency we have obtained with the VCRSI engine is around 34%. But here we are able to achieve around 31 or 32%. Similarly, if you look at the CO and CO2 emission, the CO2 emission of the engine 1, the engine 2 is very minimum, where we have implemented the optimum ignition timing and compression ratio along with the equivalence ratio that has not been shown here in this presentation. But if you see here, the CO emission is around 0.2 ppm. The CO emission is around 0.2 ppm. CO2 emission is around 7%. This is the SC and NOx emission. If you see, the NOx emission is higher in engine 3 because it is operating at high speed, around 3300 rpm, I think. Sorry, 2347 rpm. Because of that, the temperature is rising there. But in all these 2 cases, the operating compression speed is low, 1650 rpm. That's why NOx emission is higher. But if you see the SC emission, the hydrocarbon emission is low there. So finally, what you got, the brake, if you are comparing the brake power, brake thermal and brakes BSFC and the volumetric efficiency of the biogas fueled retrofitted Honda GX-SI engine is improved by 2.25%, 51% and The BT and brake BSFC is improved by 51%, brake power is improved by 2.2%, and the volumetric efficiency is improved by 32%, even if we are operating at compression ratio 10. And now if you are looking into the the emission part, engine 3 is produced lesser CO2 in the SC emission with respect to engine 1. So this is what is the final output of all my sayings. There are some conclusions, technical conclusions here. Thank you.
So you said that on the last slide you have shown that the engine 2 has an
This is engine 2.
yeah,
This is slide for engine
2, and on your last slide you have shown the comparison of the NO emission, NOx emission.
It's 1500 around 1500 ppm at CR12.
Maybe your plot, I do not understand your plot. When you go to the last slide, so here we are around 1500.
This is for MBT, sir. This is for when we are finding out MBT.
Yeah.
This is 1500 ppm. But after that, we have again went for compression ratio. With that ignition timing, we have operated the engine at CR12 and equivalence ratio, which is optimized 0.7 to 0.8. Phi is 0.7 to 0.8. And then, if you see the NOx emission here, the NOx emission at CR12 is this one now.
Yeah, still 1500.
Still 1500. Yes.
So when you go now to your last slide, 57 or so. So this this one. So engine 2, what is the NOx you have here? 300.
300.
So this I do not understand. So what is the difference?
I think it's being shifted here. It's 1500 here. Let me see.
There's also 1500. I think so.
It's around 300. Just this moment. It's like a mistake. Where it should be here only, I think.
Yeah, it's just wondering.
Yeah, so like 1500. It's.
You have said at the beginning, slide 8, that you want to capture all parameters. What do you understand with all parameters?
This one?
So you said you want to capture all parameters. So
what parameters means like parameters. What I am capturing is engine cylinder pressure, crank angle data, inlet pressure, inlet charge pressure at the throttle body, and we are calculating like mass flow rate of the fuel, mass flow rate of the air, engine load. All these are we are capturing along with the emission data. All these are being captured by using an electronic control unit. And rest what I have shown you, like net heat to release rate, mass burn fraction, mean gas temperature, we are calculating it by from the equations.
Okay. Can you show slide 11 and 11?
Yes.
So you said at 10 you have a valve which can control the inflow depending on the demand you have for the engine.
Yes.
Is there a storage system for this biogas, or what is happening? So if there is no demand, you produce all the time with the biogas, what is happening then?
There is no demand. You're saying like there is there is no load on the engine.
Yeah. So what is happening with your output or production of biogas? Do you have a storage system there, or is it just an overpressure valve and you put it to the atmosphere?
There is no any kind of system. So the system what we have built to analyze the system, like if there is no load, we can just, there is a manual valve, we can cut it down.
Yeah, okay. So can you go to slide number 12?
Yes.
Uh, maybe. Okay, we will continue with 14. Um, so here you said you have averaged over 10 cycles.
Yes.
Is it right?
Yes.
So it still look not so smooth, is it?
Yes. We are normalizing it because we have only 10 cycle data, and the rest of the graphs what we have seen for p theta here, this is 100 cycle data.
Yeah, okay.
That's why it is looking smooth.
Yeah.
And there only we are able to, because the system only we have built it, like that's why the instrument what we have used to only capture what minimum is possible.
Okay. So then can you go to slide 15? So on the right you have NOx,
Yes.
NOx formation. How have you measured the NOx?
NOx, when it is here 13, this one.
No, so which method you have used to measure the concentration?
Okay. We have an Digas 44 an analyzer. So it's for measuring NOx. I think it has a sensor which is an electrochemical sensor. And we have a device like for measuring emission. We have emission analyzer, 5 gas emission analyzer, which can able to measure H2, CO, CO2, SC and NOx.
And so is it necessary to calibrate this regularly?
Yes.
Yeah?
We have standard gases, we calibrate it.
Okay. And then finally, what is your measurement uncertainty?
It's there, but I haven't shown here. Measurement uncertainty. For emission, it is different. For other like performance parameter, it is different.
For NOx, for example.
It's like 1%, I think, around 1%, 1 to 2%
of the
measured values.
Okay.
Like we can see, if you are going to plot the standard deviation, it will be 1% up and down.
Okay, so these are my questions.
Okay, my question is on slide number 17.
17.
Because I face the same problem during while I'm doing my own biogas compression.
There.
Yeah. What is the maximum pressure that you compress biogas?
Here. 2 bar.
2 bar. Okay. But in compression, during compression, in normal compression,
you see, we are maintaining around, I think, 3 to 4 bar. Once it is stored, we are controlling it here, this with a pressure regulator, which we are able to supply with 2 bar.
But is it sufficient amount of
pressure
biogas,
drop?
No, biogas, is it available sufficient amount to compress the biogas?
You are talking about the amount of biogas. Yes. We have large balloons, which is capable of storing 2 cubic meter. So with the one balloon, we can do one experiment completely. Like you can change the pressure ignition timing. For all that, it is sufficient.
Okay. Another question is, what is the maximum temperature ignition? On your table, you showed maximum ignition temperature for biogas. It's around 600.
So it is depend upon the compression ratio what you are maintaining. If you see, this is I'll show you MGT. I see mean gas temperature. When you are operating at CR12, it goes around 1600 Kelvin here, and if you are varying the speed again, the maximum temperature here, I think this one here, MGT here, at what point you are looking, that is also important. At what angle? Maximum temperature here, when you are operating at let's say 1400 rpm, maximum temperature here it comes like 1100 Kelvin.
No, I understand, because if you are compressing your biogas at higher pressure, the temperature will rise. Because of that one, I'm asking. But at 2 bar, no problem.
Ah,
That's right.
yes, yes.
Okay, thank you.
Thank you. It's not 1700 Kelvin. This is actually pressure plot. This is temperature plot. This is MGT. This is pressure. Okay. Thank you.